Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. We now have our definitions of a maximal consistent set. In this video, I want to give you some of the interesting properties of these sets. So I've got a lemma. It's going to have 4 different parts to it, basically one for each of the propositional connectives, which will demonstrate to us some of the really interesting features of these sets. So let me bring up the whiteboard. There we are. Again, takes rather longer to get started than you might like, but there we are. So we're going to start off with some set that we already know is both maximal and consistent. And I'm going to show you some interesting properties of it. So lemma. Let lambda, remember that symbol from last time, be a maximal S consistent set. Doesn't matter what system we're talking about. This holds for any of them. Then we will prove 4 things. So for every well-formed formula phi, either phi is a member of the set or not phi is a member of the set, and not both. This is the fact that I was kind of pointing to at the end of the previous video. And then we will have that phi or psi is a member of lambda if and only if either phi is a member of lambda or psi is a member of lambda. So disjunctions only get in if one of their disjuncts are, and if one of the disjuncts is, then the disjunct itself is. Phi and psi is a member of lambda if and only if both phi and psi are in lambda. I just realized that I should have said for every with phi and psi. Arbitrary formulas, nothing special about them. Then the last one will be for implication. So if phi is a member of lambda, and you have an implication phi implies psi being a member of lambda, then, excuse me, you also get essentially modus ponens that psi is a member of lambda. So these 4 things. First, we've got that for every formula and its negation, either it is in or its negation is in, and not both. We've got 2 if and only if clauses for conjunction and disjunction, and then we have an implication clause for implication. Let's prove this. Proof of the first one. By maximality, we know that at least one of phi and not phi is in lambda. So this just comes from the definition. It comes straight out of that. Now, suppose both are in lambda. Then this means that the pair of them, phi and not psi, is a subset of lambda, and it's also a finite subset. But in any of the systems that we have looked at, because they are all based on classical propositional logic, we know that in the system S, we can prove not phi and not phi. This just is a substitution instance of a tautology, so it doesn't rely on any modal principles. So this is the case for any phi. So if both phi is in lambda and not phi is in lambda, then lambda is S inconsistent, which contradicts our assumption. So that's the first one. Now, Let's see if we can get another page on the board. How do I create a page? Add page. There we go. So our second thing, this is the disjunction case. So it's a biconditional, so we've got to prove it in both directions. Let's start by supposing that phi or psi is a member of lambda, but for contradiction, that phi is not in lambda and psi is not in lambda. So neither of the two disjuncts are. By the fact that we've just proven, we know that this means not phi is in lambda, and also that not psi is in lambda. But then the subset that contains phi or psi, not phi, not psi, this is a finite subset of lambda. And in system S, you can prove that you can't have a disjunction and the negations of both disjuncts. Again, this is another substitution instance of a tautology. So if this were the case, lambda would be inconsistent. But we know that it's not by hypothesis, therefore, but it isn't. So at least one of phi and psi has to be a member of lambda. So that's one of the directions. Now, suppose that phi is a member of lambda, or that psi is a member of lambda, doesn't matter which, but that phi or psi is not a member of lambda. Now, I bet you can see how this is going to go. It's exactly the same sort of argument. So suppose that this isn't in lambda, then by the first thing we've already proven, this means that not phi or psi has to be a member of lambda, but both phi and not phi or psi and psi, not phi or psi, are finite subsets of lambda, which are inconsistent. I will leave you to work out the exact details, but you should be able to see how this works. It's the same sort of argument. You can prove in a system based on classical propositional logic that you can't have the conjunction of psi and not phi or psi, or phi and not phi or psi. Therefore, if these are in lambda, then it is inconsistent. So this means at least if at least one of the disjuncts is in, the entire disjunct also has to be in. Now, number 3, the AND case, I'm just going to say proven analogously, because it really is exactly the same method of working out. You start with the assumption that you have the conjunction, but that you lack one of the conjuncts. You show that you end up with inconsistency. On the assumption that you have both conjuncts, but not the conjunction, again, you can show that this devolves into inconsistency, which contradicts our initial assumption. So I will leave this as an exercise for you. If you would like to put a stab at the answer in the comments, I'm happy to take a look at it. The fourth one, because it's just an implication, it's not a by implication, is a little bit easier, but it's also a little bit more interesting. So because it's a conditional, we will start off by supposing that the antecedent is true. So we suppose that phi is a member of lambda and that phi implies psi is in lambda. And then we want to show that this means that psi must be in there as well. So we start off by assuming that it's not and deriving a contradiction. But that psi is not a member of lambda. Again, by the first thing that we've shown, it follows that not psi is in lambda. But, and you should already be able to see where this is going, we then have phi. Phi implies psi, not psi, is a finite subset of lambda and is inconsistent. Now, you should be able to see why this isn't a by implication. Just because we have psi in the set doesn't mean that we also have both phi and phi implies psi. However, just because we have psi in the set, maybe you can prove that this means that you also have phi implies psi. I'll leave that as another exercise for you. But that is the main property of maximal consistent sets that I want you to have in this video. There will be another lemma in the next one, which builds on these facts. So make sure that you understand them, work through the proofs on your own, see if you can, without seeing my proof, replicate them for yourself so that you really understand what's going on. But by now you should start being able to get a picture of what a maximal consistent set is. It's basically a complete description of how things are, which sounds an awful lot like how to describe a possible world. Keep that thought in mind and join me again next time for more awkward logic. Until then, take care. Cheers.